supposed to be Singapore, dude. What the hell? But I did buy it in Okinawa. Go on. Yeah, it's a Okinawa shirt. Okay. Not this. Oh gosh, not this one. What's wrong with me? Yeah, Doppler effect. Okay, I'm expecting some really good Doppler effect question coming up in more recent years. I haven't seen it in a while already, so the one who sent me I don't know who sent me that thing. But if you look at the chat, no, if you look at Tele, or if you look at the one that I sent you in WhatsApp. So if the question is really really important, I send it out in WhatsApp, right? This one here. Oh gosh. Okay, I don't know who sent it, and I don't know where this paper came from. Like, can anybody tell me where this question or this paper is coming from? This is not an easy one. Okay, no one here sent it. Okay, someone else from the other class sent it. It was this like souped up combination of nuclear, right? Nuclear questions, and then plus this spectral line, and then plus Doppler's effect, that sort of thing. It was like one huge gigantic combined question, and this is actually something that I was looking for a while now, because if you can tell, I think it looks pretty old. I think the question is pretty old. Yeah, it didn't come from me, right? Yeah, I don't think it came from me. It came from somewhere else. I have no idea where it came from. But it is an IB. But based on the font and the formatting, it looks like pre-2016. It's one of those old questions. Yeah, and I've been waiting for something like that to come out for a while. So yeah, this is likely. I'm guessing either for your prelims or for the final IB this year. I didn't see this happen in the May paper. And if they were to, like, you were asking me, right, what happens if they ask one question where they combine a few topics into one? Yeah, yeah. So this is what we're looking at. So we're gonna do this later, since none of the people here in this class sent this out. Then we'll do this as a practice for combined, like a hybrid kind of like a question revision. Okay, and then we'll do that in a while. You got the astrophysics thing as well. It's like the main sequence thing, and they ask you like, oh, show that the sun will stay on the main sequence of this one. Didn't you get this for your CT or something like that? Nah, you did, right? Like, they ask you how long did the sun last? Eh? No? Then whose was I looking at? Was it yours? Was it? No. Wait, ACSI, you didn't have a question where they ask you about the main sequence of the sun, like how long does it? Oh no, sorry, yeah, sorry, that was a May paper. Okay, yeah. Sorry, I mixed it up. It's because your CTs and the May papers were released around the same time. Oh man, okay. Yeah, so that was a May paper. So May paper had this question. Yeah, May paper had this question. But okay lah, I guess then if that's the case, then November is not likely to come out. But May paper didn't have Dopplers, I think. So, therefore we're gonna do this. So a quick revision of Doppler. This shouldn't take too long. This is a very, very small chapter. We do Doppler sound effect first. All right. Do I really need to go through this in detail? I don't think so. Does anybody not know Doppler at all? Like, anyone who's like not sure what's going on at all? I'm pretty sure everyone knows some bit of it, right? Like, how if the sound is approaching you, or if you're approaching the sound, what do you experience due to Doppler's effect? What do you experience? Huh? Like, what is Doppler's effect all about? It's like when the sound is approaching you, or if you're approaching the sound. Not good enough. Be a bit more specific. I said approach, right? What's that? Increase in frequency, right? Everyone agree on that? Now, frequency affects what quality of the sound? Yeah, the pitch, right? Okay, good. So you understand this, right? So if it's approaching, be it the source is approaching the observer, or the observer is approaching the source. Like, if you want, I can send this out, right? The slow version of this is that the source is moving. Right? I mean, the original version of it is I had two observers, one standing in front, one standing behind, right? Then there's a stationary source over there, and then the observer is the one that's moving, right, towards and away, that sort of thing. and then what are the perceived frequencies they hear. So if you want, I can send you like the original lessons. But if you sort of like know what's going on, that's it's fine. I just try to fill up the pictures here so that it doesn't look empty here. Okay. But one thing that if you remember from my original lessons, I don't know whether or you guys watched it before your test the other time, right? Okay, so you got to remember this, okay? If the source is moving, you have to memorize what is changing. If the observer is moving, you have to memorize what is changing. This is for sound Doppler effect. So you have to memorize these two wavelength seems to get bigger and bigger. If it's moving towards the wavelength seems to get smaller and smaller, right? So that's how you tell whether or not it's like the what is changing, so the wavelength is changing. Likewise, for this one here, if it's stationary, if we look at it, right, the frequency changes because the wavelength is not changing, the speed is changing, right? The speed is perceived to change, right? The speed is perceived to either increase or decrease while the wavelength is constant. So this picture alone tells you, yeah, you look at it, the wavelength looks constant, right? And therefore this causes the frequency to change, right? This causes the frequency to change. Yeah, this is something that you like have to purely memorize. If you if you know how to memorize stuff, right? I think some of you have this skill. You know that you just need to memorize one of them because you can work out the other one, which is one of those things that I like to do. Okay, so you just memorize like one of these things here, so that you don't have to go and try to memorize, oh, this and that one there. Okay, good. And this is for sound Doppler effect. And then you have the equation here for sound, right? You have the equation for sound Doppler effect here, like this. So this one here is f prime will be the perceived frequency, f will be the original frequency, v will be the speed of the wave, us is the speed of the source, uo is the speed of the observer. Notice how the fraction is different. Notice how there's a plus and minus. When do you decide how to use plus or minus? You're okay with that? Like no one's, huh? No, no, that's fine. Okay, don't worry. So the idea here is you gotta first anticipate, or rather first infer, who will perceive a higher frequency. Like this is the source frequency, right? This is the source frequency. Like which one will perceive a higher frequency? No, this one, right? So this guy will perceive a higher frequency. F prime will be higher, okay? Will be a higher frequency. Then this one, right? This F prime will be lower, okay? So when you use this equation, you have to decide, right, whether it's a plus or minus, just so that you get a higher f prime or a lower f prime. Okay, it's based on this fraction here. Look at this. This is a fraction, right? Look at the notes there, right? It's a fraction. So it's v over v plus minus us, right? So what happens if it's a plus? What happens to the denominator? Gets bigger. So if the denominator is bigger, then what happens to the fraction? Less than 1, right? And then you multiply it. Then you know that, oh, okay. So for the low frequency, you put a plus. For the higher frequency, you put a minus, right? That's how it works. The same thing for this one as well, right? It's just that the fraction is the other way around. Now you're playing with the numerator. Please be reminded that these two equations only for sound Doppler effect. If it's like a radio wave or any other EM wave, you cannot use this equation here. Okay, you cannot use this equation here, right? So you all know how to use this equation, not the big issue. We did the train question before. We did the train accelerating before. This all came out in MCQ. Hang on, I'll go through those. We did this weird question, the girl on the surfboard as well, right? Those are all the things that we did. So we're gonna do them. I'm gonna bring up some weird like questions more recent years because my notes were created like maybe like a year ago, and then like last year some of the Doppler questions came out a bit weird. Right, I'm gonna use those as well. So first things first, constant speed, right? Train passing through platform, passing by a platform, right? The observer, like what's the perceived frequency by the observer? Right, so if you have if you were in the original lessons, I kind of like have to do this because some of you guys like completely new to this, you don't really know what's going on. So the train, it has a whistle, right? It has a whistle, and the whistle is 1000 hertz, right? 1000 hertz whistle, and the train is moving towards the platform at constant speed. So what will happen to the perceived frequency as the train passes by the platform? How does the graph look like? Yeah, yeah. So it's actually a straight line. Then there's a very steep line here like this, almost vertical steep line, and then after that another straight line like this. Okay, and it turns out that the 1000 hertz is in the middle, right? 1000 hertz is in the middle. So as the train is approaching, the perceived frequency is higher than 1000. As the train is moving away from the platform, it's perceived as lower than 1000, right? I mean, that's what the graph is. We did give a speed here, and we did do the calculations. So for those who calculated before, what was the perceived frequency at the top? What's this? 1038 hertz. And what's the perceived frequency at the bottom? What's that? 965. Okay, 965. Okay, there you go. So that's your constant speed, right? Constant speed. How about if the train was further away? How about if the train was further away? This is the classic question, like when the train was further away, the speed was still 12 meters per second, right? The speed didn't change. What was the perceived frequency when the train was much further away? What's the perceived frequency? Still 1083. Okay, so it doesn't depend on where it is, right? As long as it's approaching you at 12 meters per second, this speed, right, the perceived frequency by the person on the platform will always be 1038, right? Be it far or near, it's just louder only. Loudness has nothing to do with frequency. Right? So if you're further away, it's softer. If you're closer to the person, it's louder, but it's still 1038 because it depends on the speed. It doesn't depend on the distance, right? The perceived frequency depends on the speed. You okay with this? So even if the train goes very, very far away, like far, far away, okay, but it's still maintaining the same speed of 12 meters per second as the train is like maybe 2 kilometers away. What's the perceived frequency by the guy like of the train's whistle? It's still 965. It doesn't change, right? Unless he changes his speed. Okay, right? Likewise, we did the second the second example as well. This I'm going through this example because kind of like to make sure that students don't ask me this same question, right, over and over again, right? Yeah. So for the next one, right, the train is at rest at first. The train is at rest at first. Then it starts accelerating, right? So the initial speed was 0. It starts accelerating. Then same concept, right? The person on the platform, right, observes the perceived frequency. Right, observe the perceived frequency, like how would the graph look like? Now for the second one, you don't have to put in any values, right? But it starts at 1000, right? The graph starts at 1000. Okay, so the graph starts at 1000. Then because the train is accelerating, right, as it's going towards the observer, the perceived frequency will get higher and higher and higher, right? It's a constant acceleration, so the velocity is increasing at a constant rate. Now to be honest, I don't know whether it's a curve, but in the IB MCQ they gave a straight line, so we're just going to take it as a straight line. Okay, we're going to take it as a straight line. So as he approaches the person on the platform, the perceived frequency gets higher and higher and higher until he passes by, right, the guy. Then what will happen is that the graph will drop down to below 1000, right? The graph will drop down below 1000, and then the graph will look like that. Now, yeah, it's a bit too close to the x-axis. It's a bit weird if it's like that, right? So I'm just going to stretch it down a bit. Hang on. Yeah, something like this. But yeah, so this was the shape of the graph for the perceived frequency, right? As it's accelerating towards the guy, the perceived frequency is increasing, passes by the guy, it crosses 1,000 again, starts to go away from the guy, right? And then the perceived frequency will drop down to a low level and continue to drop as the train continues to accelerate faster and faster away now, right? So the graph will go increasing, switch down to below 1,000, and then goes decreasing frequency. Yeah. Nah, I don't know, man. So it wasn't a thing. Yeah, don't worry about it. Yeah, cause I don't think they need you to do the like the calculations for that. Any issues on this so far? No? All right. Let me mix this up a bit. Let me show you a Doppler question from, was it May last year or was it November? I can't remember. I think it has to be May because I saw it a few times already. I haven't even looked at the November paper yet. Let's see whether I can find the May one. May Doppler question, time zone 1, time zone 2. You might have seen this one though. Give me a while. Let me see whether I can pull it out. Doppler is which chapter last year? Oh man, I really forgot which chapter it was really. Doppler. Just 1 year only. I forget everything. Was it even in May? Gosh. Maybe it was November. I don't know now. I will find it. Hmm. Sorry about this. Oh, maybe it's just the thing that it was ignoring from doing. Yeah, there we go. This one here. No, this was what? November 23. Oh, okay. November 23. This was the one. Nobody asked this question in school? You okay to do this question? In a topical? My topical? Can't be though, because it's November paper. I wouldn't have put this in the. Shall I print this out for you? 25, 26. 25 and 26. I'm gonna print this out for you. Those who are online, this is the November 23. Let me print this out for the guys here first. November 23. Oh shoot, which page was it? I don't know. Ah, thank you. I should just 25, 26. 25, 26. You did this one though. Like you understood what was going on in this question. Okay, let the rest of them have a chance on this. This was in promos last year. Oh, when you were preparing for promos, is it? Okay, okay, all right then. Well, do you remember what I meant on? All right. Okay. For the rest of you, please read this question right while the printout is coming out. We're gonna start doing this question. This sound Doppler effect. Yeah, older model. Yeah, yeah. It's an older model because when it came out, we bought it, but I never wear it for 2 years. Yeah, yeah, yeah. Yeah, I know, right? Okay. And now pass to the two of you first, and then rest of you take. Yeah, go. Yeah. So A couple of interesting parts to this question here, right? Like that I noticed when I was doing this question myself. You see that they had this statement here. The turntable has, oh, sorry, the linear speed of S is much less than the speed of sound, much less than the speed of sound, right? And then it can, so the question is, why did they, does everyone have it? Okay. Like, why did they say that? Like, what's the point of saying, the linear speed of S being I mean, basically someone is put a speaker on the turntable, right, and then just turning it around, right? So the speaker at this point is going towards the frequency meter, and the speaker is going away from the frequency meter after that. Okay, but there was this statement saying that the linear speed of S is much less than the speed of sound. So it's kind of interesting because like why did they say that? Yeah. So this is an indication that you have to use the f prime, right? You have to use the yeah. You have to use the f prime equals to f and then fraction equation, right? That's your indication. If the speed of the object or the source or the observer is much less than the speed of sound, right? You're safe to use the Doppler sound equation, right? That's the Doppler sound equation. That's the indication. There was I don't know whether any of you experienced this before, but there was a question on ultrasound on blood cells. There was a Doppler effect question on ultrasound on blood cells. Does any? I think is it in my notes? Is it in my notes? Huh? Ultrasound on blood cells, is it there? Is it there somewhere? Ah, no, at the last page there you go. Right, that's the one, right? Yeah, that's the one. Ultrasound on the one there. So that question was hella confusing in my notes, right? Just for context, those who are online who are not sure what I'm talking about. Okay, let's look at the very last page, right? This one here. I had to add this in because it was really confusing. Yeah. So they say there's an ultrasound beam, right, being used to detect the blood cell, and they're trying to use Doppler effect, right, because they said Doppler shifted, right? They're trying to use Doppler effect to determine the speed of the red blood cell, and then they use this equation. So if you are familiar with the Doppler effect equations, right, you will realize that this equation is the is the EM wave one, right? So it's this one here, and that's the EM wave equation, this one here, the one with the delta F over F, delta lambda over lambda equals to V over C, right? They used they used that equation for this, which was very confusing at the time, right? Because number one, it's sound, it's sound, and number two, like why we using this equation when it's sound? Shouldn't we be using the f prime equals to f over times the fraction kind of thing? So why did we use this one? Okay, so the question itself told you that this is the equation to use, right? So in a way, don't fight it, just go ahead with it, right? But it's a legit question, like you can ask this legit question yourself, right? Why is it that we are using this equation and not the normal sound equation? What's the requirement for using the normal sound Doppler effect equation? What's the requirement again? The speed of the object must be much lesser than the speed of the sound wave, right? Okay, so it turns out that the reason why, like the background to this thing right here, right, is that the speed of the blood cell is quite similar to the speed of the ultrasound beam. So you end up you can't use a fraction, equation, since they are very similar. Okay, right? That's the whole idea. That's why this question here uses this one here. But if you don't care, right, if you just don't care and you just use whatever the question gave you, then just go ahead with it. It should be fine, right? But we did go through this in the previous lesson last year. Okay. So that's for that one. So we come back to this one here, right? Then they tell you that, oh, okay, you know what, let's look at the perceived frequency by the frequency meter, right? And the frequency meter, as expected, right, has a higher point at some point, and then there's a lower point at some point. Who that? Okay. Yeah, there we go. Okay, right. So you can see that at some point the frequency is lower and some frequency is higher. Like what was the original frequency of the wave of the sound? Was it not 440? Yeah, it looks like it's 440. Oh, they didn't say, right? They didn't say. So the first question is, um, label on the diagram for which the detected frequency is at maximum. Label this position A. It's a weird question, but isn't that just this point here? Yeah, it is, right? Okay, so that's A. Okay, that's A.
Oh, no.
Huh?
Because they asked diagram, right? See the word diagram.
Oh,
So
sorry.
on the question,
On
right,
the
it
diagram,
says
not on the
this
graph. Okay,
now both this diagram, this graph.
I see, I see, I see. Whoops. Oh, so annoying. Okay. Here is
So
A.
it would be,
It's actually there.
oh, wait, what?
Yeah,
Why
yeah,
is it not?
yeah. Why is it not up
Why
here,
is it
right?
here?
Which is the exact same question in the next question. If you look at the next question, right? In the next question, it says outline why the maximum does not occur at 90 or when 270. So if you put 90, right, you'll be like, hold up, I just put 90, right? Why is it not at 90? So the very tricky bit to this question, I was quite amazed when they came out with this question. These guys are like, like sometimes you want to think that they're assholes, sometimes you think that they're brilliant, right? Yeah. This one is a bit of both. So what happens is that the maximum is highest when the speaker is directed towards the frequency meter, like in a straight line here. Because if it's at the 90-degree mark, if it's at the top there like this, right? That's when it's a tangent to the circle. The direction is not directed at the speaker. Yeah, holy crap. That's the thing about this question, right? So this is like a weird Doppler effect question that got changed. Yeah, I mean you can. I mean basically that's what they're saying. Why is it not 270, right? I mean, oh, how many degrees is that though? It looks very suspiciously close to 270, but it's not, right? What? 300? Nah, man. What? Don't look like 300 to me. What? Oh, sorry, I have a printing error on my. Oh gosh. Oh, okay. Shitty printer. I'm gonna. Yeah. Don't worry, guys. By next week, I will have a new printer. uh, like we don't have to deal with all this shitty printing anymore, right? Oh gosh. I'm so sorry. It took me so long to go and like get started on it. How many degrees is that? Was that 285? Okay. All right. We take her word for it. 285 degrees.
So they went that deep
Yeah.
because they can't tell you which point.
But yeah, you're actually right though. Yeah, you're actually right. I mean, if you kind of like sat down to work it out, but of course, yes, the idea is that everyone thought that it was this one at first, like because it's pointed towards me. Yeah, there you go. So this is your, yeah, and then the rest of it is just your. Whoa, wow, what a way to end the paper. Was it the last question? Yeah, I think it's close to the last question. Wow, 5 marks to determine omega. The pong. Okay. Wow. Well, I mean, over the years, right, we have had these kind of questions come up before. Yeah, sorry, I'm just gonna call it. I said November is gonna have at least one or two of these, like major ass questions, like 5 marks. Yeah, I'm gonna tell you that this is the new trend. It happened in the A levels for my A level guys, like I don't know, maybe 4 years back, 4 or 5 years back, just before COVID. They had this like essay physics question. They had to explain many things for like 5 marks. Then like 2 pages down, they had like a 6 mark calculation question. Yeah, it was bad, man. So yeah, I'm not. I mean, it's a thing, like it's probably a trend, moving with times. It's a thing. Okay. All right. Honestly, I don't think I need to do it here. All right. I'm just trying to show you that when it's going away, it was like at this position. When it's going towards, it's at this position, right? Kind of like just wanted to draw the dotted lines here. I'm gonna erase this thing here at the top just so that you know. Yeah. So that's position A there, right here. Okay, position A. If you want B, B will be here and B will be here, right? So A is towards and then B is away, right? How high is frequency A? How low is frequency B? I believe you're supposed to come up with then with a simultaneous equation. I believe. I think there's a couple of things unknown, right? Is there a couple of things unknown? Oh, you don't have the speed of sound. Where? Woo! Oh, 330. Oh, okay. So what are you missing? You're missing. You're missing US. US is towards and then US is away, right? The speed of the source, right? No need simultaneous, right? You only just need one value, what? Yeah, like just F prime equals. Let's just choose one, lah. So you want towards or you want away? Let's say it's going towards, then it's F. This is for A, right? What's the calculation? F prime equals F V over V minus US, right? You can plug in everything. I think the base sorry, the source frequency is 440. The perceived frequency is this value up here, right? 330. You should be able to find US very quickly. That would be the linear speed. Why are they giving this 5 marks? They should. Could they have left out the speed of sound and forced you to do simultaneous to find V and US? I think they could have, man. They could have. That would be interesting. And don't look at me as some evil mastermind guy. Come on, man. I'm not that cruel. I just like challenging questions. Not too challenging. Yeah. If you have any friends in ASRJC, like, pity them. Sup? That's a good question. I don't think I'll be doing C5 for the whole of today. I have no idea. What do you want to do? I'm not very flexible. I got some like knots here and there. Yeah, I mean you can get it recorded if you want. I mean, what else, man? But yeah, sure. Okay. Actually, yeah. What do you want me to do after I do C5? I'm about to jump on to the next part of C5 and all. Any requests? Let's see. Let's give SGI the dips. What do you think you're missing? What do you think you're not sure of? Sama? D, huh? Okay, we'll see. All right. Part B. Oh yeah, sure. I mean, what was the A frequency that you got? Sorry, I can't see this thing, man. What's the perceived frequency at A? 4.5 what? 451? 450.5. 450.5. 450.5 is the perceived. 440 is the original. V will be 330. Then 330. 330 minus, yeah, for the approaching is minus US, which is unknown, and then you get your US, and then US is the linear speed. It's the linear circular motion speed. So this thing here has a little bit of a circular motion thing. So V equals to R omega, right? US equals to R omega, Find omega. That's it. 27.5? 27.5? No? What went wrong, Jethro? 485? Oh, okay. Careful, man. Yeah. So it's not a matter of like, at some point, guys, is careless mistakes already. So, which is great. Careless mistakes are a good sign, right? Careless mistakes is a good sign, no? Like if you tell me that I make careless mistakes, right? Okay, good, because like it's not like your foundation is completely gone, right? If you tell me that you left it blank, then I'm like, okay, I don't know. What's the answer? 27.5 radians per second. 27.5 rads minus 1. Do you not get it? You have to work faster. You need to do your math faster. You need churn out faster. You know why? Because next time we go holiday, right? My Sing dollar change to USD, USD change to Thai baht. How much is it? Oh, yeah. Yeah, you gonna go on holiday with him forever? No, right? So you only want to go on holiday with him because he's the guy who pays for everything and he's the guy who calculates everything for you, right? Then your next job is just find someone else who can do it for you, right? And then marry the guy. Oh, you have a sister? I didn't know you had a sister. Oh, okay. Okay. Yeah. So this question is one of those like weird ones. Like they try to make it interesting, but at the end of the day, it's actually just applying one. Right? I just wonder whether or not if they have omitted the speed of sound. Maybe this is a HHL paper, and then you have to do simultaneous equation to find like the speed of sound and the speed of the source. Because you have another equation at the bottom here. You can use point B as well, 430, right, when the B is going away. uh, I think there's a margin error. I think that's fine. Yeah, but you have to try to be a bit more accurate. It's not worth 5 marks. It's 3 marks. But okay, that's just me. All right. Back to it. Okay. So those who have done these questions with me before, I'm not going to do it now. Right. So there's a girl on the surfboard. I think you did this in school also. Yeah, I think in ACSI the school tutorials they did this. So if I do this is like the fourth time you're doing this. I'm not gonna do this now, right? If you want, you ask me for the recording, right? I can get you this one. We had this question, this one here. This one here is a double Doppler effect, right? We had double Doppler effect. This is a double Doppler effect. This is where you have a source at the back. He's honking his horn, right? And the guy in front is hearing it. So you need to do a Doppler effect for a moving source approaching, and then you need to do a Doppler effect for a moving observer going away, right? Then the double Doppler effect. Okay, right? We did this before, right? What was the answer for this one? For those who want to try it at home, we didn't get an answer. Oh, shoots. Okay, all right. We're gonna do it now. All right. Yeah, I mean, I did this with my year 5s this year, so I'm like, okay. Double Doppler effect. Sound. Double Doppler sound. Okay, double Doppler sound. So there's an original frequency, right? Car at the back, honking his horn, right? And the question is, let's draw a dotted line in the middle. What would have been the perceived frequency if someone that was stationary, like perceived that frequency? Like how much is the f prime? The f prime would have been f f times. So this is a moving source, So this was a moving source. Yeah. So v over v minus 3v, right? No, but the sound wave is 10v, so I better sub in 10v. So it's 10v here and 10v there, right? And therefore, what was the first f prime? What's the initial perceived frequency? How much is that? 10 over 7, 10 over 7 F. Okay? Then this sound is now perceived by the observer, but the observer is moving away. So we got to do F double prime. Alright, so we have to do a F double prime. This is like the second Doppler effect. So the F double prime is based on the F prime, right? That's trying to reach this guy. The F prime, the sound is trying to reach this guy, right? Is at this F prime. And then you multiply it by the same thing, right? So V, which is 10V over, sorry, moving observer, isn't it? So moving observer should be 10V. This one is minus UO, which is V over 10V, right? Because this time around the observer is moving only at the speed of V, right? According to the picture here, like this, right? And we have to choose a minus because it's moving away, so the perceived frequency is a bit lower, right? And therefore that's your new fraction there. So it's 10 over 7 F multiplied by 9 over 10 F. Yeah, because I sub in the F prime into this. No, there's no F. It's just 9 over 10. Yeah, that's right. Yeah, it's just 9 over 10. And therefore we get 9 over 7 F, right? That would be C as the answer. Okay? Yeah? This question is a little bit overkill for IB standards, right? This question came up in the Revision Village. If any of you uses Revision Village, or if your teacher prints out Revision Village for you, I would say that the medium questions of Revision Village are more, you know, I'll say more of the standards that you do. But isn't Revision Village all MCQ? Almost all MCQ, right? So you gotta, be very careful of that. Don't over rely on it. It's great for some questions. It's great for, I guess, some extra questions and all. And then the hard questions, the hard questions Revision Village is this. But it comes to a point whereby you actually don't it doesn't come out in the IB exam, right? I'd rather you spend the time doing more of structured questions. We good? Okay, so this was this one here. So I'm not, yeah. All right, then yeah, I guess we can get to the EM wave Doppler effect now. Okay, the EM wave Doppler effect. Now you have to be very, very careful. Okay, please be very careful that when you see this equation, you should understand that the speed of the wave, which is c, right? EM wave, right? Speed of EM wave is c. Speed of EM wave equals to c, which is equals to 3 times 10 to the power of 8 in a vacuum, right? 3 times 10 to the power of 8 in a vacuum. Yeah, that's the speed of the wave. So in this equation, v is the relative speed between the source and the observer, right? So make sure you make a note down. V here is the relative speed. I mean, did I write it there? Right, so relative speed between source and observer. So this part here for the SLs, yeah, SLs back on track. Gabriel, are you there? Okay, cool. Right, so that's relative speed between source and observer, right? And this is the equation. Now take note of this. This equation does not tell you or does not care whether or not the observer or the source is moving towards or away. This equation simply shows you the shift. So you ain't got no idea, what the shift is, like whether is it going towards or away, until you calculate the shift and then you take the original minus or plus the shift. Like that's your Doppler's effect, right? So the F prime, if you had an F prime, if you're asked to find F prime, is basically F minus delta F. Right? So this equation alone doesn't show you whether it's plus or minus. Sorry, it's actually plus or minus, right? So it's either plus or minus. F prime could be either plus or minus delta F. Right? If it's towards, then it's a plus. If it's away, then it's a minus. This equation also doesn't differentiate between the source and the observer. This equation shows you that the observer could be moving or the source could be moving. Doesn't matter, right? You just chuck in the speed, the relative speed between the two objects, and then you should be able to get the Doppler shift, right? So this is what we call the Doppler shift. right? The Doppler shift. Okay, so the question now is this. You know, back in sound Doppler effect, right, we said that if the source is moving, wavelength change, frequency change. If the observer is moving, speed change, frequency change. But for EM Doppler effect, electromagnetic wave Doppler effect, EM Doppler effect, okay, Doppler effect for EM waves, right, what is changing? This one is both the frequency and the wavelengths are changing, right? So the speed doesn't appear to change. Why doesn't the speed appear to change? Why is it constant? Because speed of light, right? So speed of light cannot be perceived to change, like at least it cannot be perceived to change more. Okay, then C. Okay, so this is your equation there. I think the most commonly used, right, application for this equation is the double Doppler effect for a radar on a car, right? So that was the question that we did here, this one here, right? This one here. Did we do this the last time round? Did I make any amendments to the question? Because I realized there was a like a little error there. This delta F given is what? Was it one way or is it both ways? Huh? This delta F is given as one way, is it? Where do you write this one way? But your delta F is 4250. Oh no, so that's no. So this is both ways. This is a total change. Yeah, it's a total change, guys. Right? This one here is a total change. Total change is 9,500 hertz. Right? Total change. All right. So I think you know what? I think I'll go through this one here because this one is such a common question, and you know, yeah. So there's a radar gun, and then there's a car, right? The radar gun is emitting a frequency of 40,000 hertz. 8 giga is 9. 40 to the times 10 to the power 9 hertz, like this. Okay, so this is your source frequency. Right. The car is, what's the car doing? Is the car moving towards or away? Hang on. Can't tell. Yeah, that was the question. I know. And the answer is can't tell. You can't tell, right? Okay, please, like this. So this is EM Doppler effect, right? So EM Doppler effect basically just, you know, you can't tell. Why can't you tell? Why can't you tell? They only showed you the change in the frequency. They didn't tell you that the final frequency received was higher than the original or lower than the original. They only show you the change. So we have no idea whether or not the final perceived frequency is higher or lower. You get what I'm saying? So since we don't know, we can't tell. We can't tell whether the car is moving towards or away. Right? Well, then that's too bad. So what happens here is that the sound wave, the radio, sorry, not sound wave, the EM wave is going to travel towards the car. It's going to hit the car. Now, whether the car is moving away or towards, right, and it has to be either moving away or towards, it cannot be stationary, right? The perceived frequency the first time here will be a certain frequency, but apparently we're not concerned about that. We're concerned about the change. So the del F, right, that's a one-way del F. Okay? Then when it reflects off the car and it goes back to the radar here, right, goes back to the radar there, that is, there'll be another del F. Okay? Right? Because that's another Doppler effect. When it reflects off the car now becomes a source and it's being observed by the radar gun. Okay? So that's why that's why I call it a double Doppler effect. Right? And this happens for all of these kind of questions. Now, the only thing that you have to be very, very careful of, and when you're doing a Doppler effect question, EM Doppler effect question, is to make sure that you understand what this means. Del F equals to 9,500 hertz, right? I would say that this is a bad on my part because I shouldn't have said this, right? I should have just said total change, right? So the total change, okay, from the initial emission of the EM wave unto the when it gets back the EM wave, right? The total change added up together is 9,500 hertz. So in this picture here, one way is how much? Like what you wrote. One way is 4,250 hertz, 4250 hertz. Okay, right? Yes, he's right. 4750. Yeah, that's right. 4750. Oh, whoops. Did we get this wrong last year? Damn. Okay, 4750. Do you write down 4750? No, 4250 also. Man, yeah lah. 9500 divided by 2 is 4750. What? Yeah, guys, come on, man. You know I don't calculate stuff in class. Okay. Then from this, we are supposed to check the speed of the car. Right? We use this to check the speed of the car. So del F over F equals to V over C. That's it. We find V. That's all there is. Yeah. Right? That will give you the speed of the car, which turns out to be what? With the new number, with the correct number now. Say what? 35.6 meters per second. Right? 35.6 meters per second. And therefore he's speeding. Right? So he's speeding there. Right? For those who had done this last year, please correct your calculations. All of you would have told me 4250, it's 4750. Goodness, I just never checked.
So this is like nearly a 1-year-old mistake.
Yeah. It's like sometimes there's like landmines around, right?
Yes.
We didn't even calculate the speed.
We didn't. Why we keep? I think I was in a rush, like your current year fives right now. I'm in a rush. Yeah, it is before promos. Yeah, and I'm in a rush with them now because I'm trying to finish up B2, B3, B4. Nuts on the ACSI. The promos is very early, right? Mid-September you're done, right? I'm already like 5 weeks away from September. I'm not finished B2, B3, B4 yet, and a lot of them are still in their la la lands, right?
So we must divide it by 2.
No, so you have to read the question really carefully. Like, what do they mean by del F? So if the question just gave you del F like this, right, and 9.5 kilohertz, right, I would say raise up your hand and ask them, clarify, right? Do you mean that this is the total change or is this the one-way change? Yeah, because it could be one-way change, right? If it's one-way change, this would be 9,500, and the backwards would have been 9,500 as well, right? Because the car is at constant speed, right? Yeah. So I would say go and get it clarified because I know this is misleading. That's why I say that in this question, I think I'll rather tell you all the total difference between emission and receive signal is 9,500. Then you have to know that you have to divide by 2. Yeah. Okay. Maybe I should just change the question. Right. I should rewrite the question carefully. Okay. Yeah. So this is the double EM effect. But because at this stage you guys have finished E1, you guys have sort of finished E1, we can now start doing all those spectral lines nonsense. Because last year if I start talking about this, you guys have no idea what I'm talking about. Maybe you still don't. Right? But at least now we can talk about it a bit now. Okay? Right. Yeah. So but last year we did do one question. I think this one was quite easy. Right? The star was emitting this radiation, then when received on Earth, the frequency perceives this, then they ask you what's the speed of the star. This one's fairly easy. You can just plug in the equation and then declare that you can't tell whether or not it's moving towards or away, right? No, sorry, you can tell. This is 1.42, this is 1.38, so the frequency is lower, right? So what can you conclude? It's moving away, right? Okay, but here's the kicker, okay? You can't tell whether the Earth is moving away or the star is moving away or both of us are moving away from each other. There's no frame of reference. So whether the star is moving away or we are moving away or both of us are moving away from each other, there's no idea, right? We just know that the relative speed is separating. You understand that? Good. You understand that? That's good. Okay, so now let's talk about this, because now this might make a bit more sense to you. I hope. What's the star made of? What's the star? What's the star made of? Yeah, what gas? Hydrogen. Hey, E5, some kind of gas, right? Hydrogen. Yeah. Okay. So as the light, how do I draw light? What color? Okay, light. As the light from a star. This is a star. Okay, by the way, right? I mean, other than from hydrogen, what else is there? Come on. Other than from hydrogen, there is also like the next most common element inside a star. Helium. Good, right? So great, right? So it's hydrogen and helium. Okay, right? When light from the star is being emitted out from the inside, like the light shines from inside, like this, like some motivational speech, right? The light passes through helium, it passes through hydrogen. Okay, right? Will the hydrogen atom absorb some of the colors? One more time, huh? Light that's being produced from the star, right, is being radiated outwards. As it's coming out, it passes through some of the hydrogen atoms, right? It passes through some of the hydrogen atoms. Will the hydrogen atoms absorb some colors? Yeah, what's the effect? What's that concept called? Or rather, which chapter, or what's all that about? What's this hydrogen absorbing some colors? What's that? Excitation. What? Spectrum. Absorption spectrum. You're saying absorption spectrum, right? That's exactly that. That's exactly what's happening here, right? So we assume that this, like, we take this as an example, right? We assume that this, right, as an example, was this is a hydrogen absorption spectrum, right? Hydrogen absorption spectrum. So as the light passes out from the inside of a star, it passes by hydrogen, right? It can pass through helium as well. I'm not saying it doesn't pass through helium. It passes through helium, but I'm just using hydrogen as an example, right? And then hydrogen has this spectrum here. Sorry, whoops, it's the one on top. Sorry, it's the one on top. Goodness, so bad at this. It's the one on top because the labels, I got confused by the labels. Okay, now how do you know that's hydrogen? Like, nobody, I mean, firstly, yes, we can more or less use science and understand that hydrogen exists in the star, right? But how did someone figure out it was really hydrogen? I think that's a very important question. It's not like someone went there to go and take a sample, right? So how did that person know it was hydrogen? Okay, so long story short is basically they took the spectral analysis in a lab, right? So you got a scientist, right, in the lab at first, right? The scientist, how do you draw a scientist? Right, you have a scientist in the lab at first, and then he has like a vial of hydrogen inside. Okay, and then basically, right, he passed light into it, and then he got a spectra. Then the spectra is essentially all the colors with black lines on it. You know what I'm saying? Yeah. So he got this spectra here like this. Let me just copy and paste this thing here. There we go. Right. So this is what he saw. Oh gosh. Okay. Yeah, you get what I'm saying. Right. So he did this in the lab, right? And he got this spectra. Then what they did was they went to analyze the light that's coming from a star, right? From our sun. Right? They went to analyze the light that's coming from the sun. Then they realized that, hey, the sun has kind of like a spectra that's very similar, right, in pattern to the one that I got on Earth in the lab, right? This is like the lab experiment, right? So this is a lab spectral analysis. I mean, what other elements can they do for in the lab? They basically can do all the elements, right? They can do all the elements. And what they do is then they take the light from a star and then they try to match the patterns, right, with all the elements. Let's say helium is another pattern, nitrogen is another pattern, oxygen is another pattern, carbon is another pattern, right? So they take the light from a star and they try to match all the patterns. That's how they tell what a star is made of, right? That's how they tell that the star is, like they could even determine whether the star is dying. What's the one key indication that the star has gone past its main sequence? What's one key indication that the star has gone past main sequence? No more hydrogen. There's very little hydrogen. There's no more hydrogen. That means it's gone past its main sequence already. It's on its late stages of life already. You know, right? So that's the idea. That's good, right? So helium would be an indication. A strong spectral analysis of helium will be a strong indication that the star is actually quite old already because all of its hydrogen is gone. Okay, so far? Can? Okay, good. Now the thing is this: we would expect, right, by theory, all stars to have, like, young stars to have hydrogen, right? And if it does have hydrogen, then it should be this pattern, correct? However, when we observe some stars, they give us this spectra instead. Okay, they give us this spectrum instead. Right, not a good color to use. Right, they give you this spectrum instead. You see this one here? Okay, notice how the pattern looks very much like the normal hydrogen spectrum, right? There's these two here, there's this big band here, then there's two small lines, and there's thin line, medium line. But they all look like they have shifted to the red side. That's why it's called red shifted. So we identify the element, or we identify the light by the pattern, right? Thin, slightly thick, very thick, two double thin, right? One thin, one medium, and then another thin, right? We identify that this is the light from hydrogen. However, when we see the same pattern, they kind of like show us different wavelengths. So what does this spectral analysis show us? Like, what does it mean about the star? Yeah, it tells us the star is moving away from from us, the observer. So this is an indication that all the wavelengths that we are like, observing from this star, all their wavelengths are kind of like shifted to the left side, right, to the red side. That's why it's called red shifted. Red shifted means that the star is moving away from us, right? Because all the colors are now a lower frequency, right? Red is lower frequency, so all the wavelengths have shifted to the lower frequency. So while we expect to see this from, like, based on the lab results, when we see the spectral analysis of a star, we realize that all the colors are shifted to the red side. So it's red shifted. Means we observe a lower frequency. Means that the star is moving away. Okay. And the other way around as well, if you notice the pattern is exactly the same, but all the wavelengths seems to be closer towards the blue side, right? Then it means that this is your blue shifted wave. That means the star is moving towards us, or we are moving towards the star. Okay, that's what this means. All right. So if you understand that, then we'll just jump into the other question. We don't need to do this one because this one here is a very weird question. I did this last year, so if you want, you can refer to the previous one, right? Just to cover this question, right? But what we're gonna do is we're gonna do that question as sent out in a group chat. Yeah, that one there, the big ass question. Right, take a quick break for now. Yeah, it's at the 1 hour mark right now. Go toilet break, take snacks. Right, help me pass the snacks around. Yeah, that's right. Yeah, so all the colors have shifted to a higher frequency, which means shorter wavelength, which means towards the blue side. You got that? Yeah. Did anybody send this question from the no one, right? None of you sent this, right?
Yeah, this is my
I'm a multi company for that worksheet. My computer has to be
For Doppler,
we'll do for like
for everything, but you want to ask questions or what?
yeah, I'll have one.
Okay. Okay. Let me print this out for everyone here. Oh no, there isn't any. Okay, are you okay to use the? Okay, no, but okay.
Hey, by the way, you know your Saturday recording last week, right?
Why?
When I was watching it, there was I don't know, but there was a few parts I think your mic wasn't working.
Is it?
Yes, because okay, but it doesn't really matter much, but because it only lasted for about 10-15 seconds each time. But basically, halfway while I was watching, there are about 4 instances where suddenly while you were talking, the mic suddenly just went blank.
Did anybody notice that for the recent recordings? That the mic went off?
I noticed that.
No, yeah, but you know, because no, the thing is that you're right, because I don't know why, but I sometimes have been getting this notification. Microphone is unmuted, but it has no signal. I don't know what's going on though. If you notice that again, let me know, cause I'm a bit worried about all my recordings then.
But it's okay that I only asked for like a few seconds. Like 10, 15 seconds.
That's not okay if let's say I'm going through something important, man. Yeah. Was it towards the start or just scattered around?
Scatter around.
Oh gosh. Yeah. I think the Streamlabs updated not too long ago, and therefore it's yeah giving me problems. What I'll do is probably I'll just maybe switch over to OBS instead of using Streamlabs from now on. Okay. Hey, your guys pass the snacks around. Let me just go use the rest. I'll be back.
Oh. You can take it. Don't feel bad. Bailey like think there's like 15 rappers here. You didn't feel I wish I could do this. I wish I could do this at home. I don't think you'll like it because it's quite calculated. All right. I need to put this screen.
Okay, I'm back. Okay.
That old song, when you went to and it got harder.
Sorry, what?
That's when you first did it. 2016 when that kind of like weird harder.
20.
Like not recent, I think. Is it true?
Yeah, 2016 was harder. 2016 was quite bad. 16 was bad. 18 was bad. I don't remember 17. Like I remember the years that the questions came out a little bit wonky. So 16 was bad. 18 was bad. Yeah. But then after that it got kind of okay. I don't remember anything that was significant. Yeah, but then 20, 20, 22, 23, 24 was bad, bad, bad all the way. Yeah, 22, 23, 24, like bad in the sense that they had like really weird questions. Like 50% were okay, and then the other 50% was like, what's going on? Like that question just now that we just did,
Yeah.
that Doppler effect, yeah, like what was that all about? Yeah. Okay, so this is everything to do with the sun. Okay. I think this one's okay. That's I don't think we need to go through this, right? But these are your E5 questions. Features of nuclear fusion, how does it maintain its equilibrium state, right? These are the nuclear fusion reactions. Then they give you the mass and they ask you what's the energy released in stage one of the reactions, right? You basically have to find the mass defect and then calculate the energy released, right? So there you go. Okay, so I'll leave that to you. I'm not gonna do it now, right? We did this not too long ago. Okay, then we have this one. Sun will leave main sequence when he has converted 10% of his hydrogen mass into helium. Oh, it's not all the hydrogen, sorry. So I don't know. Sometimes they say it's finished this hydrogen, sometimes it doesn't. It's so confusing sometimes. Total energy released in the reaction in B is this amount. The current luminosity is this. When the sun entered the main sequence, the hydrogen mass was that. Then they showed that the sun will stay on this main sequence for about this number of years. So your job is to what's your job? Your job is to find. Oh gosh, what's the value up there? It's so bad now. What's the mass of whoever took this picture? What's that? Is that 30? It looks like 30. No, it looks like 30. 30. Yeah. Wait. When the sun entered its main sequence, the hydrogen mass was 1.5 times 10 to the power 30 kilograms. So basically, you have to find 10% of this hydrogen mass, right? Basically, figure out find the mass of hydrogen. You need to find the mass of hydrogen? Basically, you lose 10% of its mass, right? So you take the mass of hydrogen. No, you can't do that. That's not mass defect. What am I looking at? Shouldn't we just take this and then divide it by that, and then that's the number of seconds we have, right? Oh yeah. We just take 3.8 times 10 to the power 26 watts and divide it by the energy of each of these reactions here, right? Energy of all the reactions there, and then that will give me a value in seconds, right? And then just convert the seconds into years. That should be the number of years that it has lasted for. Like I don't need to care about the mass for now. This is like this is luminosity, right? Luminosity is what power output of the sun, right? This is the amount of power, this is the amount of energy that the sun is producing every second. Like 3.8 times 10 to the power 26. Am I right? Yeah. And then you know, like each of these reactions here will be like this amount of energy. So the what? Yeah. Yeah. Okay. Lose 10% of its mass, right? Yeah. That's why I'm a bit lost as well. How does that turn into number of years? So number of reactions times this one. No, yeah. Wait, what? Oh no, no, okay. Gosh. I think I know something here, but I seem to be missing something. I just basically need to find out how long it will last for, right? So basically, I need to find out how long would it take to burn off 10% of its hydrogen mass, right? Yeah, okay. Okay, so for this one here, you take this divided by this, right? What does that give you though? Is that the number of that's the number of fusions per second, right? Number of B per second. Yeah? How much is that? 8.8 times 10 to the power of 37. So that's the number of reactions happening per second. Number of fusion reactions happening per second. Sorry, okay, I think I know why I'm not getting this, because this question is a bit weird. This thing here, 10% of its hydrogen mass is the mass defect. Is the mass defect. That means that the hydrogen, right, the that you will lose 10% of the hydrogen mass. So Sam, we were right just now, still, when all the hydrogen has been used up, okay, when all the hydrogen has been used up, it leaves main sequence. But this one says 10% of its hydrogen mass. This is like saying that, you know, when we do the mass effect, 10% of the original mass has been lost. Then it will it is considered as lost. It would have left main sequence. So this is mass effect. So you need to figure out how much mass defect was in the How about part D here? Sorry. Temperature 5800 was the peak wavelength. What's that about? Wave displacement law. And then the Doppler effect for this one, the E, this one here. So that's what they mean when they say that spectral line of hydrogen has a wavelength of 656.2797 nanometers. The same spectral line emitted from point P, right, on the sun, right, has this wavelength when it's measured on Earth. Then they ask you explain this observation. So how do you explain it? So like, you know, on Earth here like this, and then point P, the light is shining towards Earth like this. Okay, so why is it that the spectral line is 656.2797 on from the sun, but then yet when we measure it, it's 256? So what's going on? So the original wavelength was this, but the perceived wavelength is this. What's that? This Doppler's effect. It's a shorter wavelength, right? So does it tell you that point P is moving towards or away from Earth? Towards, right? Point P is moving towards. Why? Because it's a higher perceived frequency, right? It's a lower perceived wavelength. Okay, then they ask you to calculate the period of the revolution of the sun. Right, so this thing here again, you can use your del F over F equals to V over C, then your V equals R omega. Then you can use omega, find omega equals 2 pi over T. Then you can find your period there. That was it. That's a weird question. Let me figure out what they meant by the nuclear mass one. But yeah, this is the Doppler effect part of the question here. Any issues? No issues. I go through another scenario, right? There's another scenario which I think I haven't seen in a while as well for Doppler's effect. This thing called binary stars. Yeah, binary stars, right? So the idea here is that most stars out there in the sky, they're actually binary stars. So for binary stars, is like you taken down the notes for this one. I'm gonna leave it to you to go and calculate. The answer is there anyway. Okay. So there's a binary star system, right? It's a binary star system, and then the Earth, right? The observer is here like this, right? So what we understand is that the binary star system, the stars are orbiting each other. Okay, so how about the light that is coming towards us, right, versus the light that is right from the other star, right? So this is the light coming from this star here, and then the light that's coming from this star here like this. Yeah. So we would see one side, the color will be red shifted, and then we will see the other side, the light will be blue shifted. Okay. Yeah, you just take this picture down. I mean, that's all there is. I guess the equation itself, the question itself is not that difficult. So I just want you to be aware of the scenario. Can Yeah, that's all. Right, because this star here is moving towards us, and then this star here is moving away from us. Okay, I'm pretty much done with EM Doppler even. I don't really want to drag this out anymore because I think some of you are quite good at this. So now the question is, what do we do next? That's a big question because I didn't plan ahead beyond C5. No, they did say that. I mean, for the SGI guys said what D1 and D2, huh? D1 and D2. Anyone else having problems with other chapters or like rigid? Huh? A4? Hmm? Induction? Have I revised A4? Yeah, A4 I sent before. Unless you want me to do questions only. A4 I sent the videos already. Yeah. Wait, when was the last time I revised D? So You know what? Let me do one A4 question and one D4 question. How about that? Sorry, one A4 question and one D1 question. I got the numbers mixed up.
Are you gonna go for deep?
No, not now. Soon. Yeah, lah, soon. How about this? This is a CT that came out this year, the year 5s. TP lah, yeah lah, TP. Yeah, I'm very sure it's a TP. No, man. Okay, you know what? I'm just gonna. Okay, let's look at this. Oh, not dark enough. Yeah, okay. Is there enough full scale? Can you just help me pass the full scale over? I'm just too lazy to print out, and I don't want to risk like making the printer die halfway. Yeah, just tear off some and use it. It's fine. That's from our one of our partner centers, TSV at Beauty World. There. Yeah. You need it? Hey, pass one back to her. Yeah, just take it and tear it. It's fine. Sonia does math, but she does it more for Sec 3, Sec 4 math. Yeah. You know? No? Did anybody go to TSV? This center. She's quite popular among the secondary schools. Yeah. But she caters to the west side. Okay, there's a ring of mass. It's a bit small, yeah? Okay. Boom. Okay, big enough now. Ring of mass m 0.32 kg, radius 0.25 meters, accelerated from rest by a constant torque of 0.20 newton meters. Moment of inertia of this ring is mr squared, right? Then they ask you calculate the angular acceleration of the ring. Yeah, simple stuff lah. But you know what? Let me ask you a couple of things. How do you accelerate this ring from rest with a torque? Like, give me an example. How do you spin it? Yeah, sure. So you have a ring, right? So the idea here is that you have a ring. Okay, there's a ring like this, and then you apply a force to the side like that. You apply a force to the side like this. But how does a torque of 0.2 newton meter, like, like how is it created? You apply a force here, right? Like, where's the center of rotation? The center of rotation would have been here, right? Okay. Actually, this is not the only way to spin the ring, right? You could have spun it. You could have spun it like you could have taken a ring and could have spun it this way, right? Then the moment of inertia would be different, isn't it? Yeah, it would have been different, right? So why are we supposed to assume that the center of rotation is in the middle? Okay, so the center of rotation is in the middle, okay? I think this question the teacher came up with it himself. In fact, can I ask you this? Can I ask you, could you find the force that caused the torque? Could you find the force that caused the torque? Yeah, you can, right? I mean, the torque is here, you got the R here, right? What if I tell you that it was not just one force? What if I tell you it was a couple? Correct, right? So the idea here is that the question can change if it was a couple. If it's a couple, then you got two forces. Yeah, like it will be the combined moments, right? Like the combined moments of this force and distance and this force and distance will be this torque of 0.20 newton meters. It depends on what the question wants, but I'm just helping you visualize that this is the force that causes it to accelerate. But before you go any further, so in your mind, right, you're thinking that you apply the force and then it spins, right? But is the force constant? Is it a constant force though? Or is it a one time you hit it one time then it spins? Is it a constant force? It's a constant force, huh? So a constant torque means that the force is applied constantly. So it's not like, you take something, right, then you hit the wheel one time. It's like you apply a force constantly. How would you do that though? One of the ways to do that is actually to tie a rope around it. Like kind of like, let's say you have a rope around it like this, right? And then you pull the rope. Then if you pull the rope, then there will be a constant torque applied on the ring. Sure. Yeah. Spinning tops. Yeah.
You mentioned why you assume that
Oh no, I didn't. It's like I mean, from the way that the question is asked, it's like they didn't give us much of a choice to, yeah. Pretty sure that the teacher missed out that point that you could rotate the ring another way like this, right? So it's not always like that, but okay lah, right? So sorry, what?
Yeah.
Is the alpha 10? Is it 10? Let me see. 10 radians per second squared, right? So alpha is 10 radians per second squared. Wait, have you calculated it? Huh? Careless mistake again? Yeah lah, careless mistake again. Okay, so alpha equals to, well, I mean, what's it? So torque equals to what? I omega, right? Right, I alpha, sorry. I alpha, sorry, I omega is angular momentum. And it's just torque over I lah, right? Torque over I. And therefore you get 0.2 over mr squared, right? So 0.32 times 0.25 squared, right? If you remember from the A4 videos, are you supposed to memorize any moment of inertia? Right? Yeah. Huh? Yeah. No. Actually, not even for this ring. Like you're not supposed. There's only one that you're supposed to memorize, which is what? Particle, right? Point mass. So if let's say you have a turning point and you have a mass r and this m here, right? Then you need to know the angular, sorry, the moment of inertia of this point mass around this pivot. This is your pivot here, right? So that will be, yeah, mr squared. So moment of inertia equals to mr squared. Yeah. So this is 10 radians per second squared. Okay. Right. No issues there. Right. Like if you're copying this, Audrey, this one here, this part here, this is the part that your students are supposed to memorize. If you haven't gotten this, you better go and catch up on the videos, right? I can't possibly revise everything. You have 25 chapters. Yeah. Right. I do not have 25 more weeks. Yeah. Right. So go back and just catch up on the recordings. Okay. Next, no, I'm not done yet. So they ask you what's the angular velocity after 5 seconds. What's the angular velocity after 5 seconds? Right, angular velocity. That's a lame question. You just take this and try 5 lah, that's all. Right, what's the angular velocity after 5 seconds? Like how fast would it be rotating after 5 seconds? Just take this 10 times 5, 50 radians per second. That's not the question I'm trying to get at. There is a part of this question that I was not too happy on, but don't know whether IB will test. No, it's whether or not you are supposed to know this. Okay, let me show you the question. Okay, down here, it says a solid disk of the same mass and radius as the ring is accelerated by the same torque, right? Then they ask you, compare the angular impulse delivered to the disk and the ring during the first 5 seconds. Yeah, they didn't give us the moment of inertia. So you have to infer lah. You have to infer. That's the annoying part. Yeah, that's the annoying part. So this part here, I'm not too sure whether IB will actually ask you to kind of like infer. Yeah, exactly right. Okay, so right here, right now, we learn this at least. Okay, what does moment of inertia mean? Reluctance to rotate. Moment of inertia means reluctance to rotate. Okay, like you got to think about moment of inertia as like what's harder to rotate. Right? Is it easier to rotate a certain way? Is it harder to rotate a certain way? Let me show you an example. Okay, let's take this tube for example. Right? Let's say this is a cylinder. right? The cylinder. Those online, I'm not too sure whether you can see it. So you could rotate it this way about its long axis. You could rotate it this way, or you can rotate it this way, right? The question is, which one is harder to rotate? Like, which one will require more effort to rotate? So do you rotate it like this? Is it easier than rotating it like that? Right? I mean, this one here, the axis in the middle, right, of the length, right? This one is harder to rotate. This is harder to rotate. So the moment of inertia when you rotate it like that is higher. But then for the same object, if you rotate it this way, the moment of inertia is different. So moment of inertia depends on the mass of the object, the size of the object, as well as how are you rotating it. Okay, so for this particular case here, the disc and the ring, you got to think about this. Everything is the same, mass is the same, size is the same, right? But the disc and the ring, which one is easier to rotate? Which one is harder to rotate? The disc is what? Why is it easier? So we think about a disc, right? Let me try to draw a disc. Let me try to draw a ring. I don't know how good would I be at this, but yeah, I'll try. Right, so this is a disc versus a ring. How do you draw a ring? Yeah, something like that lah. Okay. So just imagine that, okay, same size, right? So this is a ring and this is a disc, right? I mean, we're gonna have to assume that the axis of rotation is the center of the ring and the disc, okay? Otherwise, this question is gonna be like, so annoying, right? So this center of this and the center of rotation. Turns out that the ring and the disc have the same mass, right? So the disc and the ring has the same mass. Yeah. They're saying disc is easier to rotate. Why?
Oh no. I just say that because when I was like doing the econ, like this like half.
Okay, you just memorize the formula, but we kind of like, that's why I'm going through this question, right? I think that this one is the thing that kind of like stumped a lot of my year fives. I mean, as well as like kind of like probably you guys as well. So which one has a smaller inertia, a moment of inertia? Okay, so when I ask you which one has a smaller moment of inertia, I'm asking you which one is easier to rotate. Okay, now the ring is harder to rotate because, right, the mass is concentrated at a distance away from the center of rotation. Like all the masses is like this far away from the center of rotation. The further the mass is away from center of rotation, the harder it is to rotate. Yeah, I mentioned this last. Okay, but okay, fine. Right. I sometimes I don't know whether I mentioned this. Right. So the further away the mass is, the harder it is to rotate. Okay. So which is the case of this rod here. Right. When I'm trying to spin the rod this way, the mass is like on this side and on this side. Like it gets progressively further and further away from the point of axis, the point of rotation. So it's harder to rotate now. But then yet when I try to rotate it along the mid axis, right, the long axis, right, when I try to rotate it, the mass is all very close, right? They're all very, very close to the axis, the center of rotation, right? So that's why it's easier to rotate like that. So the moment of inertia of this will be much smaller than trying to do it like this. Okay? So for this one here, for the same mass, since they have the same mass, right, the mass is more or less quite spread out. Okay, the mass is more spread out towards the center of the rotation, right? In that sense, I'm trying to draw like the mass is more spread out. Okay, not focused, not concentrated at a distance away. So the disk has a smaller moment of inertia, right? So like you said, you memorize that the ring has what? Mr squared, right? And you're saying that the disk has half mr squared. Okay, so in a sense, like she's not wrong. It's just that you're not supposed to memorize this, but okay, right? So the mass is more, this one here, the mass is concentrated, right, at r away from axis. Okay, then this one here, the mass is more spread out. Okay, so if you were to encounter a question like this, you should understand that the disk of the same mass has a smaller moment of inertia. It's easier to rotate the disk. Okay, now if you then look at this question, right? They did ask you, right? So they ask you for the angular impulse, So um, angular impulse is torque times what? T? Yeah, impulse is torque times T. So they have the same torque, they have the same T. So angular impulse, the amount of angular impulse that they both get actually is the same because they have the same torque and they have the same amount of time applied, 5 seconds, right? So impulse will be the same. But the final kinetic energy will be different, right? The final kinetic energy will be different because, you know, the eye of the disk is smaller, right? And it has greater final kinetic energy. Why though? How do you prove this? That it has a higher kinetic energy. Ke of rotational Ke is what's the equation? What? I R squared over 2I. L squared. Oh, L squared over 2I. Oh yeah, yeah, right, okay. Yeah, you're using the sorry, yeah, Ke equals to P squared over 2m equivalent equation, right? Yeah, that's right. So since they have the same L, the one with the smaller I will have a higher Ke. Yeah, that's right. Sorry. I was thinking of half m omega squared. But yeah, so L squared over 2I because we're comparing the same angular momentum. Was it the same question? Did you get this question before? No, right? Okay. Well, good stuff, guys. I mean, sometimes I forget myself. But yeah,
But you can still use half I omega squared.
that's the problem. If you use half I omega squared, you have an issue. Half I omega squared, right? The I is smaller, but I know the omega will be larger. But the question is how much more, right? You can work it out. You can work it out because but the thing is that you don't know how much I is smaller, right? We only know I is smaller because she said that it's half I r squared, right? But you're not supposed to know, you see? Yeah. So yes, that's right. So the best way to compare will be this L squared over 2I, right? So this has smaller I, and therefore it will have a larger Ke, right? Okay. So I have a big decision to make on Tuesday. By before Tuesday, like what's the next thing I'm going to do? I did set one paper out. I gave you all the what? Which paper? November 2016, is it? Yeah, November 2016. 2016, yes, that's right. It's in the 2016, it's in the shared drive. I sent the message out last night, I think. Was it last night? How late? I can't remember. I think I fell asleep at 2:30 on my desk. But yeah. All right. So I think I sent out November 2016, right? Trying to get the MCQ done. Okay. Okay. Huh? What? B4. B4. Yes. I will wait for SGI to go for their thing first, then I'll do B4. Right? Thermodynamics. Right? Because some of them are asking for thermodynamics. Yeah. Can you drop me a message, Tisha? Just say remember to revise B4 after SGI goes for on break. What? The question. What's that? No, it's not the start. The main sequence. Oh, you did the calculation, is it? Okay, take a picture for me and send it to me. I will go through this later on and another time. Yo, wow, no way, dude. I can't do that. What? Okay. Wait. So what do I revise? Am I supposed to do kinematics, dynamics, A2? Am I supposed to do that? So you keep asking for D4. What? I did it before, right? What else? What else am I missing? Huh? Okay, so D and E I did it in June, right? Oh gosh, okay, can fine. I'll start doing D1. I don't know, huh? Again, right? Yeah, sorry. Hey, come on. What do you want me to revise then, guys? Last year's stuff. Last year's stuff being, I just did all of C's. How about B1, B2, B3? Do I need to do that? Oh no, B1 I did, but I didn't do B2. I didn't do B2 yet. Greenhouse gas. Then B3 is ideal gas. And then B5. Oh yeah, okay. I think I better do that then. Yeah, I did, but then I think some of you are still really bad at it. B5. B2, B3, B5. Then after SGI goes for their prelims, then I'll do B4. Because I did B4 with them. I did it over a weekend with them. I had like 2 lessons with them. I did B4. But I'll do B4 for the rest of y'all, right? Anything else? Anything from A? A3? Work energy power? So y'all don't need collisions, right? Y'all need collisions? Huh?
Yeah, you already went through that.
Oh, circular motion. Do y'all need me to do circular motion? Circular motion. Okay, can somebody keep track of this for me? Sorry, Trisha. Okay, circular motion, B2, B3, B5, and then B4 after SGI goes for their prelims. When SGI goes for their break. I think that's all I can squeeze in. But I still need y'all to do the November 2016 paper one. Okay? Right? I'm just a bit afraid of some of your classes, your teachers are not going through anything, then y'all don't do any practice. Then I get a bit worried. Because that's what happened last year. Okay, and you like, I don't know whether you saw my message in Telegram chat, guys. If you feel like your pace is like okay, that means you're not going fast enough. You need to go a little bit faster. You need to feel like you're getting out of control a bit, right, for all your subjects. Okay, but then maintain at that out of control speed. Like imagine you're a rally car. Okay, that very bit before you go off the edge. Okay. That's what the pace you should be at. Okay, if you're comfortable, you gotta get yourself uncomfortable. Okay, see you guys. Bye. Those online, thanks very much. Mark, enjoy your holiday. See you, man.
He's going overseas.
He is overseas. He's in Bali. He's doing in Bali hotel lobby. Someone he tells me.